So welcome back students. In this particular video we will do a revision of all the major topics which are covered under unit 2, and unit 2 deals with the semiconductor devices. So our main focus will be first of all to introduce what are semiconductors and what are the other types of materials. So if we talk about an introduction of semiconductors, as we know there are three different types of materials which are conductors, insulators and semiconductors. So in the diagram which has been provided here, we have been provided with the energy band diagram where we have a conduction band and the valence band. So if we will see regarding the conductors, which are also called as metal, so metal is an alternate name for the conductors only. The valence band and the conduction band here, they are overlapping. So overlapping means that the electrons which are available in the valence band, they are already part of the conduction band. And the concept goes like this, that if we want a current, then electrons must be available in the conduction band only. Then only the electrons will be free and they can start conducting. We can have a conducting material. So in case of metals, the valence band electrons are already available in the conduction band because of the overlap. So they are good conductors of electricity and they can conduct easily. So this is one extreme end of conductivity, and the second extreme end is insulators. Insulators are materials that do not conduct at all, and you can see the third diagram here which corresponds to the insulator. So we have a valence band and the conduction band, and in between there is a very huge energy band gap, right? So the difference between the valence band and the conduction band is the energy band gap, Eg. So this value is very high value. It's a value that cannot be fulfilled when we apply the voltage. Suppose you are applying certain voltage, so that voltage is not enough that the electron which are available in the valence band may shift towards the conduction band. That is not possible. So that is the second category and the second extreme. So we have conductors which are extremely good at the conduction, and we have insulators which do not conduct at all. Now in between we have a material that we call as semiconductors, and the example is given here, the diagram is given here. In semiconductors, what we have, again we have a conduction band and we have a valence band, but in between them the energy band gap available is very small. It's a very small energy band gap. So it means when we are providing a voltage, whenever an external voltage is provided, there will be the possibility that we can shift the electrons from valence band to the conduction band, and once we have electrons available in the conduction band, then it will start conducting. So semiconductor is an in-between material that can act as insulator also if we talk about the 0 Kelvin temperature kind of thing, and it can also behave as a conductor if suppose we apply the proper voltage and some other techniques like doping and all will be applied. So then you will see that semiconductors can conduct in a good way. Now we can discuss what are the different types of materials that can be given as an examples of conductors, insulators or semiconductors. Now regarding conductors, the examples are gold, copper, silver, aluminum. They all are good conductors of electricity. Similarly, the examples for insulators are like rubber, glass, wood, mica and etc. And regarding semiconductors, the most important example is the silicon, because around 95% of the material that we build in electronics, it is made of silicon only. Then the other materials are germanium, we use selenium, we use gallium arsenide, like in the LEDs that we have currently that we use at our home, they are made of gallium arsenide. So these are the different types of materials which can be given as an example for semiconductors. What are the advantages of semiconductors? So there are a lot of advantages. The first one is that because the semiconductors are very much small in size, so they make your device compact. Suppose in the labs you must have seen diodes, or you must have seen the BJTs. They all are very small devices, right? So they can make your device compact. Second one is that no heating is required. Actually, the point number 2 advantage is given with respect to the older devices that we were using before the advent of semiconductor devices. Like we were using the tubes that time, and those tubes required kind of heating so that we may turn them on. But once we have semiconductors, then such concept is not required, because all we need is just the voltage to turn on the devices. Then semiconductors occupy very less space, and that is logical because the size is very small. So if we talk in terms of printed circuit boards that we have currently in all the electronic gadgets, so you can have a lot of devices available on a given board. Then semiconductors require low voltage operation. It means the voltage that is required to run semiconductor devices is very small. Like suppose if we talk about the motor, suppose if we are having motor at our home, so that motor we need around 220 volt, or if suppose we are having a transformer at our home, that transformer will also require 220, because these are the electrical devices. They are electrical devices. While as if we talk about diode, if we talk about suppose BJT, so these are the devices that can conduct when you are providing a voltage of around maybe 3 volt, 5 volt, things like that. So that is why we say that low voltage operation is required. And the last point is low power consumption. Now coming to the disadvantages of semiconductors. So the first point is conductivity changes. Like we have seen this behavior in conductors also. Like if suppose the resistance is changing with respect to temperature, then we use a formula like this, that if temperature changes then the resistance also changes. So that thing is happening in the semiconductors also. So that is one disadvantage. Second one is you need extra components for stabilization, which actually is a solution for the first problem. If suppose your values are changing, then what we will do, we can stabilize the things. Like in our homes we use stabilizer. If your voltage is fluctuating and you are running the AC and all, so you will be using stabilizer. Similarly, you will need extra components so that you can stabilize the current or the voltage. So that extra hardware that you are using is a disadvantage, because extra hardware means more money is involved. And the third point is semiconductors are easily damaged. Like suppose you have a diode and you are giving excessive voltage, or suppose we have an LED and for that LED you are giving excessive voltage. So what will be the result? The result will be that due to the excessive heat, these devices will get burned out, so they will not be usable. So what we had to do, we had to simply throw them and you had to replace it with the new device. So that is what they are saying, it gets easily damaged because of the high voltage. Or sometimes what might happen, once we are soldering the devices into the board, you might have the case that due to the excessive soldering or the excessive heat that has been produced due to the soldering, the device can also get damaged. So we have a simple question here, what is the resistivity of a semiconductor? It lies in between, right? It is in between the insulators and the conductors. Now the next topic is what are the different types of semiconductors. So mainly we are having two broad types of semiconductors, intrinsic and extrinsic. Intrinsic is also called as pure, while as extrinsic is also called as impure. Then furthermore, extrinsic semiconductors are of two types, one is P type and the other one is N type. Now first of all we will discuss intrinsic semiconductors. Intrinsic semiconductors, as I said, they are also called as pure semiconductors. Why they are called pure? Because they are made of a single material. Like suppose I told you what are the examples of semiconductors. The best example is the silicon first of all. So if we talk about a structure where we are having only silicon atoms available, okay, like everywhere it is surrounded by silicon only, and we can continue this process like this. So this kind of structure will be an intrinsic semiconductor because no other element has been added except we have a silicon over here. Now the properties of the intrinsic semiconductors are electrons and holes are created by the thermal excitation. It means whether that thermal excitation is due to the voltage or it might be due to the temperature being increased. So then what it will result in? It will result in the electrons and holes. And the number of electrons and holes are equal. It means number of holes and number of electrons are equal in an intrinsic semiconductor. And the third point is conduction is very small at the room temperature. Now why the conduction is small? Because if we see this example that I have drawn here, so you will observe that in silicon, if we talk about the atomic number, so it is 14. right? 2, 8, 4. So how many electrons we have in the valence shell is 4. Okay, so that is what I am showing here with these 4 lines. So we have 1, 2, 3 and 4. So these 4 electrons are making bond with the other neighboring silicon atoms that we have over here. So it is a kind of a covalent bonding that we are having, and this structure will continue for the whole material, whole crystal that we are having. Now because all the electrons are properly having a covalent bond, so we don't have any free electrons, so there are no free electrons, and due to that what happens, the conductivity of the material gets decreased. So the same example that I was explaining you is given in the slide. So there are no free electrons if you will see this diagram. Okay, but what may happen, you might increase the temperature. Due to the increase in the temperature, what might happen, there might be some bonds that might broke, and due to that some free electrons might get reduced, might get produced, but even then the conductivity remains very less. The next part is the concept of hole current. Now if we talk about the normal conductors, we have current only and only due to electrons if we talk about the conductors or metal. But when we talk about the semiconductors, we say that the conduction happens because of two charge carriers. One is electron, which is similar to conductor, then the another one is the hole. Now we should also know that the holes are nothing but it is one concept that actually doesn't exist. Hole does not exist in the reality, but what is this concept that we need to understand, and the summary is given here. Holes are nothing but the missing electrons. Okay, the absence of an electron is called as a hole, and we assign it a positive charge. Like electron is a negative charge and we are saying hole is the opposite of that, so we are assigning it a positive charge. And sometimes we the whole concept is easier for us to explain the things because it is easier to keep track of missing particles. It is very simple, like if suppose we are taking attendance of 72 students in the class, and suppose only 3 students are absent, right? So instead of tracking all the students who are present, they are 69 in number in this case, it is easier to track these 3 absent students, so it means remaining all are present. In the same case, suppose we have 72 electrons now, okay, and 3 electrons are absent and 69 electrons are available for us. So instead of tracking these 69, it is easier to track these 3. So that absence of electron, if suppose we are dealing with, so we can say that can be defined in terms of hole. And you can see here there is an example given. You can see we have a valence band here, we have a conduction band here at the top, and we are having some electrons available. So the moment you can see in the figure 2, the electron which was available at position A is moving to the conduction band. So what has been created here is a vacancy. And why this vacancy has been created? Because there is an absence of an electron. There is an absence of an electron. And why there is an absence of electron? Because this electron has moved to the conduction band. Now see what is happening. This electron that we are having here, because there is a free space available towards its right, so it is moving towards right. So the moment when it is moving towards right, so it is creating a vacant space here, okay, that is visible here. So why there is a vacant space here? Because it has moved here. And in the same way, in the last diagram, what are we showing? Because there is a vacant space being created at this position B, so this position, that is position C electron, is moving towards B, right? Now because C has moved towards position B, so what has been created? We have created a hole, absence of an electron at position C. Now if you will observe this diagram, so what is basically happening? The electrons are actually moving towards the right, but it might also look that if we are tracking the holes, then it might look to you that holes are also moving, okay, because first of all hole was here, now it is moving towards this side, now it is moving towards this side. So what is happening? We can also say that if electrons are moving in the right direction like this, if electrons are moving in this direction, then holes are also moving in the opposite direction. So that is why, because they are opposite in nature, so we assign the positive charge to the holes. Now this question is easy. What is the valency? It is 4. What kind of bonds do we have in semiconductors? Covalent. Now one very important concept, like we said in intrinsic semiconductors, because all the electrons are properly bonded, the valence electrons, so there are no free electrons. So to increase the conductivity, there is one very important concept in semiconductors. That concept is called as doping. Now what is doping? It is written, it is a process of adding impurities to the semiconductor. Now impurities does not mean that you are adding some kind of dirt and all. That is not there, that is not the concept. Impurities means you are adding the elements which are different than the intrinsic material. Suppose we had a silicon, now you are adding in this silicon maybe the pentavalent impurities, means those elements which are having valency of 5. Okay, penta means 5, valent means valency, so valency of 5. Or it might be the case that we are having a silicon and we are adding to it trivalent impurities, means those elements which are having valency of 3. Alright, so we can have a pentavalent impurity or we can have a trivalent impurity added to the silicon, and this process is called as doping. Now first thing that might again come in the MCQs certain times is that you should know the examples. What are the examples of pentavalent impurities? What are the examples of the trivalent impurities? So for pentavalent impurities, the examples are bismuth, antimony, arsenic, phosphorus. They are all elements from group 15. Similarly, examples of trivalent are indium, gallium, boron, and so on. So they are all from group number 13 elements. And in the pentavalent impurities, what happens, because we have 5 electrons, so what will happen? Suppose we have a phosphorus, right? So phosphorus is having valency of 5. So 4 will make bonds with the silicon, correct? Now what will happen to the 5th electron? This 5th electron will be free, because all the 4 have already made the bond. In the same way, let us talk about the trivalent impurity. Suppose boron. In boron, what we do, we are having valency of only 3 here, right? So what will happen? The 3 atoms that it is having, they will make bonds with the silicon, but this one will be free. The silicon that we are having here, this electron is not making any bond, so it will create a vacancy over there, right? So in this way, the alternate names of pentavalent impurity is donor. Now why it is called donor? Because it is having extra electrons, so it can donate that electron for the conduction purpose. And trivalent impurities are also called as acceptor. So why it is called acceptor now? Because it can accept an electron because of the vacancy that is available in the boron. Now extrinsic semiconductors, as I said, it can be of N type or P type. So it is very simple. If we are adding pentavalent impurities, then it is called as N type extrinsic semiconductor. And in the same way, if we are having a P type semiconductors, it means we are having a silicon and we are doing a doping with the trivalent impurities, so it will become P type, right? So there are some examples given in the diagram, so you can follow that also. Like if you see this particular slide, so it is showing you arsenic, which is having 5 electrons, so 4 of them are making bonds with germanium, because germanium is also a pure semiconductor, and 5th one is free, so it can help you in making the conductivity better. In the same way, there is one more example given here of boron. So in boron, what is happening? 3 is the valency, so 3 are making bonds. There is an absence here, so this absence is a hole, so this electron may come and jump here, so hole will be created here, and so on. So in this way, conductivity can again increase. So we have some simple questions. When a pentavalent impurity is added to a pure semiconductor, it becomes, so it is a pentavalent, so it will become N type semiconductor. Similarly, N type semiconductor is, now you have to remember this very important concept, that whether we are talking about an intrinsic semiconductor or we are talking about the extrinsic. When I say extrinsic, it covers both P type as well as N type. So all of them are electrically neutral. Okay, so you might think that N type might have more number of electrons or P type have more type of holes. It's not like that. All the atoms will be, all the type of semiconductors will be electrically neutral. So the option C is correct. Now once we understood what is p-type semiconductor, what is n-type semiconductor, then what we can do, we can just combine this p and n, and we can create one very important device that is called as a diode. So our next topic is the PN junction diode. It is a material that can be created by just combining the p-type and the n-type. So what is happening, we are having suppose p and n, and we are bringing them together. Now what is happening? Please note down, if it is a p-type semiconductor, there are two type of charge carriers. One is majority and the other one is minority. In p-type, majority charge carriers are holes and minority charge carriers are electrons. In the same way, if it is an n-type material, then again we have majority charge carriers, minority charge carriers. Majority charge carriers here are electrons, minority charge carrier here are holes. Now if we will look at the diagram, in the diagram we have something like this shown. So it is representing the hole, and then this kind of thing is representing electron. So if you will see now this p-type, so you can see more holes are shown, the white spaces, and electrons are shown less in number. Similarly, if we talk about n-type, we have been shown more number of electrons and less number of holes. So the very first step that happens, the very first thing that happens when you are combining p and n is the diffusion process. And diffusion is a natural phenomenon. This is a natural phenomenon for which you don't need any kind of voltage. There is no voltage required for this purpose. And what will be the result? The result will be, the diffusion means there will be a movement of charge carriers from higher concentration to the lower concentration. Right. So if we see, we have majority of holes here in p and it is in minority here. So holes will move from p to n. So holes will move from p to n. In the same way, the electrons will also move from n to p. So this movement of charge carriers is called as diffusion. And for this there is no need of voltage. And this is what we also refer as a zero bias or no bias. In a diode, there are actually three types of biasing. One is called as zero biasing, then forward biasing, then reverse biasing. So in this diagram, what are we just showing is that because of the zero bias, what is happening? The electrons were moving here, the holes were moving here. This process is the diffusion process, but this diffusion process will not happen indefinitely, means it will stop after certain time. Because what will happen, when these electrons are moving from n to p, they are leaving behind this positive immobile ionic charge. Okay, that is shown with this plus and a blue color. In the same way, when the holes are moving from p to n, what they are leaving behind is the negative immobile ionic charge, which is being shown here. Right. Now due to this, what will happen? The time will come when these electrons will try to move. Okay, these electrons will try to move and cross the junction, but they will be repelled. They will be repelled by the negative immobile ionic charge. Right. So this and this, they will repel. In the same way, the holes and the positive immobile ion holes, they will also repel each other. So in that case, what will happen? They will not again diffuse. So there will be a moment when the diffusion is going to stop, and that particular thing that we have created over here because of depletion of charge carriers is called as depletion region. So why is this called depletion region? Because we have depleted them of the charge carriers, okay, the moving charge carriers. And it is also called as a barrier potential, because you need now certain potential, you need now certain voltage in order to overcome this particular barrier that has been created over here. Then further we have forward biasing. Now the question was, once the barrier was created, how to remove that barrier? For that we have a forward bias. So what is the concept of forward bias is, if suppose you are connecting the p-type semiconductor with positive terminal of the battery and n-type semiconductor with a negative terminal of the battery. So this is positive and this is negative. So p is connected with the positive terminal, n is connected with the negative terminal. So this kind of connection is called as forward biasing, right? Now in this forward biasing, what will happen? Suppose my voltage is first of all 0. Now I am gradually increasing it. Suppose 0.2, 0.4. Now what will happen, because this voltage is very less, it will not be sufficient to overcome the barrier, because it is written here it is a barrier potential. Now the value of the barrier potential, it varies as per the type of material we are having. Suppose we are talking about silicon. For the silicon, the barrier potential is how much? It is around 0.7 volt, and for germanium it is around 0.6 or 0.4. Now what will happen, once we will gradually increase this voltage, we will see that once the voltage is around more than 0.7, then we will see the this barrier that we are having here, its depletion width W will become less and less, and due to that what will happen, there will be again the movement of charge carriers from N to P and P to N, and that will result in the current being flowing. Alright, and that behavior we can see here also. Once we will increase the potential, suppose it is 1 volt now, so this positive terminal of the battery that we have here, it will attract what? It will attract electrons. So electrons are majority in the N, so they will be crossing the junction. So more the voltage we are applying here, more will be the electron movement from N to P, and we are having negative terminal of the battery here, so more number of electrons will be here, again replenished. Okay, so in this way we will have a free flow of current when we have a forward bias. So because current is increasing over here, so we can also say that the resistance of a diode when it is in forward bias will be very less. In ideal condition, we replace it with a short circuit if it is a ideal condition. Now you can see the question. A diode has a forward resistance of the order of ohms because, as I said, current is high. Then we have a reverse bias also. In reverse bias, what happens? If we have a p-type semiconductor here and we have a n-type semiconductor here, so we are doing the biasing, we are connecting it with the battery in the opposite way. Means p side is connected now with the negative terminal of the battery and plus is connected with the positive terminal of the battery. So in this case we shall see that there will be no current. Now see why there will be no current, because once suppose we are having a voltage of around 1 volt or 2 volt. Now this is a positive terminal of the battery, so it will attract what? Electrons. Where are we having electrons? We have electrons in the N region itself, right? So we have electrons here only. Let me show with the red. We are having electrons here only. So these electrons will be attracted towards positive of the battery, positive terminal. So they are moving here. Or you can also explain like this, that this is a p-type semiconductor. In p we have what? Holes, and this is a negative terminal of the battery, so the negative terminal of the battery will also attract holes. So what are we observing? Instead of crossing the junction, where are they going? They are going in the opposite direction. So the width of the depletion region is going to get increased, right? It is going to get increased more and more. And if suppose we are having more depletion width, it means there is no possibility of any current. So we can say current is almost zero. And if current is almost zero, then what is resistance? Because resistance is V upon I and I is almost zero. So R is tending to infinity. Means the resistance in a reverse bias of a diode is a very high, and practically it is of the order of mega ohm also. Now you can see the question, if the positive terminal of the battery, so we have a battery suppose, is connected to the anode. Now you should know that in this diode, the positive side is represented here, and this is called as anode, and this is the negative terminal, this is plus, this is minus, and the negative terminal of a diode is called as cathode. So anode is connected with what? Positive terminal. So it means the connection is nothing but the forward bias connection. In the reverse bias, there is one more point, that we have already understood that actually there is no current, but a very small amount of current also flows in the reverse bias, and this is due to the minority charge carrier. Okay, I will explain that. Now see, in this P, the majority are holes, but we have also read that in p-type semiconductors we have minority as electrons. In the same way, we have read that N region has holes as the minority. So when we are applying the reverse bias like this, so what is going to happen? This negative charge, this negative part of the battery will attract holes, right? And this positive terminal of the battery will attract the electrons. So we can see there is a movement of charge carriers with respect to the junction also. So due to this minority charge carriers, we will be having a very small amount of current, that is also called as the reverse saturation current. This current is called as a reverse saturation current that flows in the reverse bias. Then we also need to understand that as we said that ideally once you are providing a reverse bias, there will be no current, but that does not mean that we will increase this voltage indefinitely to any value. Okay, suppose somebody is giving 30 volt, which is a very high voltage, and expecting that no current will flow. Okay, that is not possible, because every diode that we are bringing from the market, they are having some breakdown voltage. Alright, so suppose the breakdown voltage of a diode is 15 volt. So it means we cannot apply voltage more than 15 volt in a reverse bias. Otherwise what will happen? Your diode will be having a breakdown, and after breakdown that diode will get damaged and it will be of no use. So the small current that develops in the reverse bias is the reverse saturation current. Then in this diagram we are showing the different symbols of a diode, and if you see these symbols, they are related to the practical diodes that we use in the lab, because anode and cathode needs to be identified. So if we talk about the practical diodes, we will be having one silver lining. That silver lining indicates negative side, so the other opposite one will be the positive side. Now the next topic is VI characteristics of a diode. Now you had to understand the VI characteristics in the forward bias as well as the reverse bias. Now in the forward bias we understood that once your voltage is very less than 0.7, then there will be a very small current, because we had a depletion region over there. So once your voltage will be crossing 0.7, then we will see that there will be a very high current that flows, and this is an exponential graph. And if you remember unit 1, I have told you there that diode does not follow Ohm's law, because they don't have a linear curve. So you can see here, when we are plotting the voltage and the current, the graph that we have is an exponential curve. Alright, so this is the forward biasing graph. You have to show that small current is flowing up to 0.7. 0.7 is the knee voltage. Okay, this is the knee voltage where the graph is taking a turn from less value to a high value. So that knee voltage is what? It is a minimum voltage that is needed to turn the semiconductor device on or on. Alright, to turn the device on. Suppose for silicon, I told you this voltage is around how much? 0.7 volt. Then if we talk about the reverse bias, in the reverse bias what we understood, that if we keep on providing the voltage, the current will be almost zero. So that is what is being shown in the graph also, and you have to show it as zero until what? Until the breakdown. Like I told you, there is a breakdown voltage, the maximum voltage that we can apply to a diode in a reverse bias. So after that what will happen? There will be again, once the diode will be getting damaged, then what will happen? There will be a very high current that will flow in the diode. So this graph simplifies this graph is telling you the complete VI characteristics of a diode in the forward bias as well as the reverse bias. So when you are plotting this in the exam, please keep track of the x-axis and the y-axis. The x-axis represents the voltage and y-axis represents the current. So we have here VF means forward voltage, this is the forward current. So forward voltage, forward current is the graph for forward bias. Then we have reverse voltage VR and the reverse current IR, and this graph is for the reverse bias. Now ideal diode is the one which behaves as perfect dash when forward bias. Now see, the word is ideal being used here, and I told you when we are having a forward bias, because in forward bias we have a current that flows, so ideally it will behave as a conductor. And in the reverse bias what will happen? As we have read in the explanation, there is no current because the charge carriers are moving in the opposite way, so it behaves as an insulator. So for this question, as it is given for ideal conditions, the answer is A, conductor. Now if you want to know whether the diode is working or not, then what is the procedure? The procedure is very simple. All we need to do is bring one multimeter from the lab. So once we will bring the multimeter, we will keep it in the ohm meter mode so that we can measure the resistance. Then what we have to do, as we have identified the anode and cathode of the diode, plus and minus, so the two terminals of this multimeter, the red and the black, so what we will do, we will connect first of all the red with positive, black with negative, so it is a forward bias case, right? So what are we expecting? The resistance in the forward bias must be what? Very less, correct, because there is a current, there is a high current here. And similarly, when you are reversing the terminals, like you can see here, what are we doing in this diagram? In this diagram, what are we doing? Let us see again. We are having here plus anode, then this is cathode, but we are doing it in the reverse bias. You can see the red is connected with negative right now, so it is a reverse bias. And in the reverse bias, what should happen? The resistance must be very high. So if these two conditions are met, that the resistance in forward bias connections are less and the resistance in the reverse bias connections are very high, it means your diode is okay. And if any one of the conditions is failing, then in that case it means that your diode is not fine. It is it needs to be replaced with some other diode which is working fine. Then coming to the applications of a diode, so as per our syllabus, we will be covering rectifiers. Clipper and clamper are the other applications of a diode which we can use, but they are not part of our syllabus, so we will not cover them. So rectifiers will include half wave as well as the full wave, so let us discuss them. And rectifier is a very important topic as far as the conversion from AC to DC is concerned. Rectifier is one of the steps for doing that. So what about half wave rectifier? So what do we have here is a diode, and we are providing some alternating voltage. So alternating voltage, as we have read in unit number 1, it has a positive half cycle, it has the negative half cycle. Then we have to see what will be the behavior of a diode, right? So in order to understand this, we have to understand the positive and the negative half cycle. So let us suppose we have a diode and we are in the positive half, okay? So let us suppose we are in the positive half. So in positive half, we are giving positive voltage here and we are giving the negative voltage to the next side, means here. So we are giving a voltage like this, okay, although it is an AC. Now this, because this is a forward biasing, so in ideal condition it will act as what? It will act as a I can say conductor. So in that case we can replace it with a short. So what will be my diagram in that case? In that case my diagram will be, we have a voltage, then we have a diode which has been shorted, and we have a RL. So what will we observe? If this is VI and this is VO, so what will be the voltage VO? And okay, now you see this point and this point, they are same nodes. This point and this point, they are same nodes. So we can directly say that V out is same as V in. Okay, so it means suppose your voltage input is changing and it is like this, so your output will be also following the same procedure. Okay, practically it will follow this after 0.7 volt, because 0.7 is the built-in potential of silicon. But ideally, if you are showing the graph, you can start the graph from 0 itself, right? This is the behavior in the positive half cycle, that V out is V in. This is for the positive half. Now what will happen in the negative half cycle? In the negative half cycle, the negative voltage is provided, and when the negative voltage is provided, as you can see in the diagram, this becomes negative. Okay, so we have a diode with, this is plus terminal, this is minus terminal, and we are giving negative terminal of the battery with positive, with the anode. Okay, because I have told it already, in a diode this is plus and this is minus. Now what are we observing here? It is a reverse bias being given, because minus is connected to plus and this is connected with the minus. Now in the reverse bias, it will act as what? Insulator, means it will be an open circuit. Okay, so you can note down these points. If the diode is in forward bias, it will act as short circuit. If the diode is in reverse bias, it will act as open circuit. So its equivalent diagram would be something like this. We have VI here, then we have diode, but diode is open, and we have here voltage V out across the resistor. Now what is V out in this case? Because it is an open circuit here, so current will not flow. When current will not flow, what is V? V is I into R, because current is 0. So what is V out? Also 0. So it means in the positive half cycle we have voltage same as V in, and in the negative half we have a voltage equal to 0 only. So it means if we are plotting, suppose we are plotting voltage also and the current also. Suppose I will show here, this is V in for us. So how to plot the output? So for the positive half, what was our conclusion? V out and V in are same. So we will plot it like this for the positive half. And what happens in the negative half cycle? V out is 0. So until we have this negative half, the voltage will remain to be 0. And the same thing will continue for all the cycles. So this is the you can say half wave rectifier explanation. Then we have full wave rectifiers. In full wave rectifiers, what we do, we have an output in the positive half cycle also, in the negative half cycle also. Okay, if we compare the input and the output. Now how is this made possible? For this we use multiple diodes instead of a single diode, and basically there are two methods by which we can achieve the full wave rectification. The first method is the center tapped full wave rectifier. Now let us understand this. Now center tapped full wave rectifier means we are using a transformer with center tapping. Center tapping means, because see, if the normal transformer we talk about, in the normal transformer what we have two conductors on the primary side, right, and two conductors on the secondary side. Okay, these are called as primary coil, these are called as secondary coils. This is a normal transformer. Now this is a center tap. Center tap means there is a tapping. There is a tapping from which side? From the center also. It means from the center of this secondary we have one more line coming. So it has two wires on primary and it has three from the secondary. So we have first line, we have second line, and we have the third line. And why it's called center? Center means if suppose we have number of turns on this side, suppose 100. So what is the half of 100? 50. So means when there is a 50th turn, we take connection, we take a tapping from the 50 of that. Okay, number 50 turn. So it becomes 50 turns here, 50 turns here. So it is a center tap. Now what happens when we take the connection from the center? If we look at the potential there, that potential has been here grounded in this particular diagram, right? Now how does it work? For that we have to again understand what is happening in the positive half and the negative half. Now note down, we are having here two diodes D1 and D2. Now what will happen in the positive half cycle? Positive half cycle means we are providing the positive voltage, right? So upper side will be plus and the lower side will be the minus. Now see students, when we are providing a voltage in such a way that this side is plus, this side is minus, then it means in a diode also, because of the mutual induction, the diode 1 will get here plus and this minus voltage will be here. Now because this is plus and we have here positive terminal is connected with the anode of the diode, so plus is connected with plus, so it will act as a short circuit. Similarly, we have a diode here, but what is happening? We have a negative connected with the anode, so it will be reverse bias. Okay, and then what we have a resistance here also connected at the center. We have a resistance here connected. We can draw it like this also. Okay, this connection RL. Now what will we observe? We will observe that there will be a current which will flow in this circuit. Correct. Now in the same way, if we talk about the negative half cycle, in the negative half cycle you are providing the negative voltage. In the negative voltage, what will happen? This side will be minus and this side will be plus. Now see what will happen when we are giving a voltage with this minus and this plus. So according to the diode also, what will happen? This will be minus, this will be plus. So this minus will make the diode D1 off, means opposite will happen, and diode D1 will be on. Why? Because this is plus here and plus will be connected with the anode of the diode, so it will be short circuited, and we have a resistance also, and we will complete the circuit. Now in this case what will happen? Again there will be a flow of current across RL. Now please note down, the current in the RL in this case and this case, they are both flowing in the same direction, that is this one. Okay, so it means if we have to plot the things, suppose this is my input voltage, then what will be my graph for the this output? So what have we observed? Whether we are in the positive half or the negative half, it will conduct in both ways. Only difference is if it is in the positive half, the diode D will conduct and we will have a path, and in negative half diode D will conduct, and again it will have a path. So in both the cases our output and input will be same. Okay, and we are showing it for the ideal condition, so we are starting the graph from the 0. Now there is one more method that is called as bridge rectifier. With bridge rectifiers also we can have a full wave rectification. Now what we will do in this case is we are using 4 diodes which are connected in the form of a bridge, right? Now let us see what will happen if we are giving a positive half. In the positive half means we are connecting this one with plus, this one with minus. So due to the mutual induction of transformers, this will be plus, this will be minus. Now this is plus means this is plus and this is minus. Now analyze, students, it is very simple. If suppose we have a diode, and in diode we are having here plus terminal. So plus is connected with the anode, so it means it is forward bias. This is what we will be looking at. Or suppose we have a diode where this is connected with negative, it means negative is connected with the cathode side, so again it will be what, forward bias. So in this way I am going to check the status of D1, D2, D3, D4. Now let us draw the diagram. Here I will show it for positive half. I am showing it for the positive half. So we have 4 points, 1, 2, 3 and 4. So this is plus, students, and this is minus. So what will happen to D1? We have plus connected with the cathode of the diode, so it will be reverse bias. We have plus connected with the anode of the diode, so it will be reverse, it will be forward bias. Then we have here negative terminal of this connected with the P side, so again it will be reverse bias. And we have here negative with the cathode side, so it is positive. Okay, so this is my diagram. Now you can see this is where input is given, this is where input is given, and this is where output is taken. Now will there be a current flow? Yes, we have a positive terminal here, so current will flow like this, like this. Now there is a path here, and then it is moving like this, and it is closing the path. So we are having a current across the resistor R. Now the question is what will happen in the negative half cycle. So if we see the negative half cycle, then what will happen? This will be minus, this will be plus. So accordingly this will be minus and this will be plus because of the mutual induction. Now we have to again check the status of all the diodes as per this minus and plus. So let us draw these 4 points. Now see D1, we have negative with the cathode, so this is forward bias. We have here also plus connected with the anode, this is also forward bias. Similarly, please note down D1 and D2. You will see minus with anode, so it is reverse bias, and we are having here plus with the cathode, that is also reverse bias. So it is completely opposite of the upper diagram, and then we will draw our input. Okay, so what is the story right now? This is minus, this is plus, this is the condition. Now the question is, will current flow? The answer is again yes, because current will flow. This is positive here, this is minus, so it will flow like this, across the resistor, then it will move like this. It is completing the path. But again the point to be noted is, if we look at this resistor, the current is flowing in the same direction in both the cases, right? In both the cases it is moving like this, right? And it is conducting in positive half as well as in negative half. Now if we plot the waveform, so if we have suppose input like this, now what will be its corresponding output? As we said, it is conducting in both the ways, so it is again same as the previous topic diagram, means it will conduct in positive as well as in negative. We are plotting it with respect to V in, and this is my V out. And why are we saying that V in is same as V out? It is because there is no other element here, right? It means all the nodes we are having here, suppose this is node A, so it means this is also node A, and if this is node B, then this is also node B. There is no other resistor there, so obviously V out and V in are same. Then one more type of special diode we have, that is called as a Zener diode. In Zener diode, what is the difference? There are some things which we do here that makes this diode bit special. First of all, we have seen that a normal diode conducts in the forward bias, does not conduct in the reverse bias. But Zener diode we use in the application that it can be used as a voltage regulator. It can be used as the voltage regulator. and for that you need to connect your diode in the reverse bias only. So the first important point is that the Zener diode can operate in a forward bias as well as the reverse bias, and in fact reverse bias is more essential, more helpful, because that particular mode only we use in the application where Zener diode is acting as a voltage regulator. Now the question is how it is made possible, in the Zener diodes. For that there are some reasons. First of all, what we do is we do a very high doping, and second thing what we do is that the thickness is also decreased. If we look at the thickness of P and N, that thickness is also reduced. So due to these constructional changes that we perform, what happens is that the Zener diodes can also act in the reverse bias and they can act as a voltage regulator. So if you see this diagram, in this diagram we are showing a practical diode. So this N, this negative part represents N side, so this is the P side. So that is how you can identify the anode and the cathode of the Zener diode, and this is the symbol being shown. Like normal diode we show like this, now you have to show it like Z, so it represents the Zener diode. So what is the depletion region of the Zener diode? It is thin, and it is thin because of the high doping that we do in the Zener diodes. Now the next important topic is the transistors. So transistors were invented in 1947 by three great scientists, Bardeen, Brattain and the Shockley, and for that they were also awarded as the Nobel Prize in 1950. So it is one of the remarkable inventions in the field of electronics. Now if we have to understand BJT, first of all you will understand its basics, its constructional details and all. So BJT can be of two types. First of all, transistor can be of many types. When we say a word transistor, transistor is a very broad term. When we talk about the transistor, transistor can be BJT or it can be MOSFET. Okay, as per our syllabus we have to cover these two. Now BJT stands for bipolar junction transistor, MOSFET stands for metal oxide semiconductor field effect transistor. Okay, this you will cover later on in the video. Now BJT, why it's called bipolar? Because the current that we have in the BJT is because of two polarities, two polarities. And what are those two polarities? Electrons and holes, right? And the second important point is, when we talk about the BJT, they are three terminal devices. Okay, let us suppose if we talk about a diode, what was diode? Diode was a two terminal device. We had anode, we had cathode, P and N. But BJT is a three terminal device that can be NPN or PNP. So if we have to make a rough diagram here, you can see like this. This is NPN or it can be PNP. So it is a three terminal device. Suppose this is emitter, this is collector, and this one we call as base, right? So what is emitter, what is base, what is collector? Emitter is a point, it is a terminal which will act as a source of electrons, right? Then what is base? Base is a material that can control the flow of current, and collector is the point where all the electrons get collected. To understand this in a better way, we have one analogy as well of this water. So what is this water? What is this tap that is being connected here? This tap is suppose source of water, right? Source of water. So this tap is nothing but an emitter, which is the source of electrons. Then suppose we have to collect all the water here. So we will be using some bucket here, right? So that bucket is nothing but the collector. Like the role of the bucket is to collect all the water, the role of collector is to collect all the electrons. Now the third important thing is the base. Now we have here what? Knob. We have here the knob of this tap. So once we are rotating this knob, what can we do? We can control how much water will come out, whether you want more water coming from the tap or the less water coming from the tap. That you can easily control by rotating this knob clockwise or anti-clockwise. So that knob is nothing but the base. So with this base, what can we do? We can control the flow of electrons reaching from emitter to the collector, right? So this way you can understand what is the role of collector, base and emitter. And second important point is, out of collector and emitter, the emitter will be having more number of electrons and or you can say holes, depending upon we are discussing PNP or NPN, and collector will be more in area. Okay, we will be discussing all those points. Here we are then showing the symbols. If we show the symbol of PNP, then what we have to do, suppose this is the transistor symbol. Okay, if the arrow is going outwards, then it is NPN, and if you are showing it like arrow going towards inside, then it is PNP. Okay, that thing you can note here. This is PNP, this is moving outwards, so this is NPN, right? Now in the construction details, some very important points that will actually make us understand why transistor is different from a diode. Or suppose sometimes the question will come, if suppose we connect two diodes, okay, back to back, will it create a transistor? So how can we answer this question? Okay, the explanation lies here. If the three regions, collector, base and emitter, is compared, we follow certain things like the doping of emitter must be greatest, followed by collector, and then followed by base. Now what is the reason of this? The reason is because emitter has to be the source of electrons or the source of holes, depending upon what is the majority, is it PNP or NPN. So that will be decided by the doping that you are doing in the emitter region. Then the second highest doping we have to do for collector, then for the base. And second point is, and if we talk in terms of surface area, the area of collector should be highest, followed by emitter, and then followed by base. And now see, every point here is logical. Why is it that we need that collector should have more area? It is because all the electrons are ultimately collected by the collector, right? So output is also taken from the collector only. So when your transistor will be in the working condition, where will be the heat generated? Heat will be generated obviously at the collector only, because we are taking output from there only. All the electrons are coming there only. So that is why we need more surface area, so that we can dissipate away this particular heat, right? That is why its area must be highest, followed by emitter. Then why is it that the base must be very less doped, or why is it that it must have the smallest area? The reason is because once we are having electrons here, okay, these electrons want to reach to the collector. So once these electrons will reach the collector, before that they have to pass the region of base also. And in base, if suppose we have more doping, then what will happen? We will be having more holes here, and once electrons will be passing here, so what will happen? This electron and this hole, they will combine, and once electron and hole combines, that process is called as recombination. And in the process of recombination, what will happen? They will lose their existence. They will lose their existence, and they will release energy in the form of heat. So it means this electron will not be able to reach to the collector then if we have more recombination. So what is our aim? Our aim is that the process of recombination should be least. And when is it possible? It is possible when you will be having less number of holes in the P region over here. So that is why we are doing less doping. And second thing what we are doing to ensure that maximum electrons reach to the emitter, to the collector. So for that what we are doing is we are having its area also less, because if suppose area is more, right, area is more here, suppose this is emitter, this is base. So when these electrons will be moving here, they will be having holes, so they will stay in this base for a longer time. So electron will at some time combine with the hole. So again it will result in recombination, and that will again result in the loss of electron. So less electrons will reach at the collector, and less electrons at the collector means what? It means that we are having less amount of current also, so which is not good. So that is the reason why these two things are important. And now because these two things are followed in the construction of a diode, it is not possible that two diodes connected back to back can create a transistor, okay? Because they can ask you one logical question. Suppose this is one PN diode and this is one more PN diode like this. Now they will tell, if they will connect these two, can it create something called as PNP? You have to say that the answer is no. Why? Because of these two reasons. We don't have in the BJT, when we talk about emitter, base and collector, we don't have equal areas, we don't have equal widths, we don't have equal doping. So these things will be sufficient to prove that we cannot create a transistor from diodes. So you can answer this question. The base of a transistor is lightly doped. Next question, the element that has the biggest size in a transistor is collector. A heat sink is generally used with a transistor to prevent excessive temperature rise. Okay, because if there is a more heat getting generated, then you might have to use these heat sinks also, which will help you to dissipate away the excessive heat. Now suppose we have to explain the operation of the transistor. Then what we do is, we have taken one example of a common base configuration. We have here emitter, base and collector, right? Now what we have to do, emitter base junction, it must be forward biased. So how are we doing it as forward bias? N side is connected with negative terminal of the battery, P is connected with the positive terminal of the battery. So once we are providing here a voltage, suppose 0.7 or more than that, then what will happen? We will see that electrons that are available in the N region, they will cross the junction and they will move towards the P side. So electrons will flow from emitter to base. Then we have also understood that we are using some concepts. We are ensuring that the recombination does not happen in the base. Now, so that recombination does not happen in the base, what measures have we taken for that? We have the least doping for the base, right? We have done the least doping, so that very less number of holes are available over there, and we have also made its width also least, so that electrons can stay there for a very small duration. Because of all the measures that we have taken there, what is the result? The result is that practically when we see, only 2 to 5% of the electrons recombine, which is a very good thing. Suppose it means out of 100 electrons, we hardly have a case where 2 to 5 electrons will recombine. It means 95 to 98 electrons are successfully reaching towards the collector, right? But what we observed till now, once we are having an emitter base junction, we have given forward bias, so electrons were moving from emitter to the base. But we do not want electrons to remain in the base for a longer duration. For that, we have to again provide one voltage at the collector base junction. We have collector and base, we are giving here a voltage, and this is a reverse bias voltage. Now why reverse bias voltage? Because we are having electrons here. Now these electrons must be moving towards N side. So how can you push the electrons towards N side? For that you have to provide the positive terminal. So if we connect here positive terminal of the battery, so what will happen? So suppose we are providing here 3 volt, 5 volt high voltage. So this positive terminal of the battery will attract the electrons. So electrons which are coming in the base because of the forward biasing, these electrons will move further and they will move towards the collector. And due to this, we will have a complete current from emitter to base, base to collector, and there will be a free flow of electrons. Okay, so it means once we have to explain the operation, you have to understand what is emitter base biasing, that is forward bias, and collector base biasing is the reverse bias, and how the movement of charge carriers is made possible from emitter to the collector. And then we have a relation that total current that we have, IE, will be equal to IB plus IC. So the base current in a transistor is about 2 to 5%, right? Most of the majority carriers from the emitter, they do not recombine, right? They do not recombine. They pass through the base region and up to the collector, correct? In the same way, you can also explain the PNP operation as well. Or the story you have to start with holes. Like in NPN, we talk about electrons. Here you have to repeat the same thing with respect to holes. Then regarding the modes of operation, you should know that in a transistor there are two main applications of a transistor, of a BJT. One is it can act as a switch. Switch means we can use it in the digital circuits for on and off. Okay, because in digital it is all about 1 and 0. On means 1, off means 0. So if you want to have a transistor that acts as a switch, then you have to operate the transistor in these two modes, cutoff and saturation. Cutoff means off mode and saturation means on mode. Now the condition of emitter base junction and the collector base junction in that case should be, cutoff means both are reverse, saturation means both are forward bias. The second application of a BJT is amplifier in analog circuits. In that case what we do, we have to connect our transistor in the active mode. This is the mode we have read in the operation once we were discussing the operation, where emitter base junction was forward bias and collector base junction was reverse bias. Now what will happen if you do the reverse of that? Okay, reverse active means emitter bias reverse bias, collector base forward bias. In that case it tells that there will be a performance degradation. Why? Because in that case what will happen, collector will try to have a role of emitter and emitter will try to have a role of collector, but because constructionally that will be the opposite of what we have done, so that is why it will result in the performance degradation. So this is never used, right? So we have either we use transistor as a switch, so then we have to use these two modes, or we can use transistor as an amplifier. For that we have to use the active mode. So the question is, when the transistors are used in digital circuit, they usually operate in saturation and cutoff. Configuration of a transistor, there are three ways we can connect a transistor. It can be common base, common emitter or common collector. Now the common word is being used with respect to one of the terminals based on which terminal is common. You have to see which terminal is common between input and output. Suppose if you see diagram 1, this base is connected here also, here also. So if you see this side, this is input side and this is the output side. So what is base? Base is in the input side also, output side also. If you see second diagram with the same logic, there is an emitter here. Emitter side is connected to the input also, it is connected to the output also, so it is common emitter. And if you see this third diagram, we have a collector side here, and collector is common between input and the output. So in this way, once we are connecting a transistor, we can connect it in the mode of common base, like the operation that I explained to you, that was common base. Similarly, we can have common emitter, then we have to configure our transistor like this, or it can be common collector. Now each of them are having its own advantages and disadvantages, so that we shall see maybe in some other classes. Now what is the relationship between alpha and beta? We define two parameters, alpha and beta. Alpha is defined as the ratio of IC upon IE and beta is defined as the ratio of IC upon IB. Okay, the ratio of collector current by emitter current is called as alpha, which is the current gain, and IC upon I beta, IB is also called as beta, which is also a current gain. Now what are we doing? We are putting these values here, and what we can do is we are getting one relation that relates the value of alpha and beta. So these relations are given here. So we need to remember these relations in case some numerical is being asked. Suppose in this question alpha is given, beta is to be calculated. So you can use a formula, beta is alpha upon 1 minus alpha, as you can see here, alpha minus 1 minus alpha. So alpha value is 0.9 and 1 minus alpha is 1 minus 0.9. So it will be 0.9 divided by 0.1, so the value will come out as 9. Alright. Suppose the question is IC is 100, I is this much, and what is the value of beta? So in this case what you will do, first of all we will find what is the alpha value. You can do that way. IC is equal to alpha IE. So alpha will be what? IC over IE. So it will be 100 upon 100.2 milliampere. Both of them are milli. So what is 100 upon 100.2? So you can use calculator, and this value is coming at 0.9980, right? So then what is beta? So beta is alpha upon 1 minus alpha, so we can write 0.9980 divided by 1 minus 0.9980. So again you can use calculator, so this value is coming out as 499. So the answer is B, 500. So students, will be stopping over here. I will be covering the MOSFET and the op-amp in part 2 of this video. So till then you can revise all these topics, and in case you are having any questions, any doubts, you can ask in the comment section. I will be very happy to answer those. So that's it for today. I will see you in the next video. Thank you all and have a nice day.